Hello everyone. This is week number 2 in Cognitive Science 501, Algorithmic Structures in Cognition at Middle East Technical University. This is the spring term 2020. And in the first week, I gave you an introduction about how we can study form, meaning together using computation as sort of the cement for doing these together. And this is going to tie up to handling uncertainty as we process meaning and form together in various domains of cognition, like language, vision, planning, or any kind of organized behavior you can think of, like music and dance and others. And we've been doing this by first distinguishing content and structure, mainly because although content can be quite ambiguous, when you see structure, when we look at structure, although we see ambiguity in structure as well, the kind of ambiguity that you get in structure seems to be different than the ambiguity that you get in content, because although there can be structural ambiguities like attachment ambiguities. I'll give you an example from, like, I saw the man with the telescope. Depending on who has the telescope, this could mean different things. But given one interpretation, if I have the telescope and the man doesn't, then you got one interpretation. Given the other interpretation, that the man has a telescope and I don't, there's another interpretation. But given the structure, it seems like the meaning of the structure is disambiguated somehow. So we have to be clear what it means to be structure, what it means to be content, what it means to be ambiguous, and how do we get structure in the first place to be able to talk about this ambiguity. And we're going to do that in the form of formal language theory first, so that's going to take us to formal study of structure. And the term is sometimes ambiguous, so maybe I should make a distinction in the beginning. Now, when we say formal study of structure, it could mean different things, and although they're related, they are different. So formal here could mean different things. This could mean like related to form, rather than content. It also means rigorously studying the relation relations in the form itself. And usually when you're going to rigorously study something, you're going to need mathematics. And I'll try and show you, this is going to give you like formal language theory. Right, and that's why we're going to use formal language theory for studying form in a rigorous way. The reason why we're studying rigorously is because we want to be able to see the limits of what we're talking about. Okay, so although we're going to use mathematics, we're going to tie it up to its computation. Therefore, we're going to talk about actually computer science. So formal language theory is one of the sort of pillars of computer science. And sometimes it's considered just mathematics, but if you recall from my early introduction, We're going to do these structures formally mainly because they're going to lend themselves to very transparent computation. So in one sense, we are doing description, but descriptions themselves don't compute. So we need to see how we translate these descriptions into computational devices. And those devices themselves will see the limits of the thing as you study. So in that sense, computer science is not really mathematics. It's, of course, it uses mathematics just like any other science, but of course, you're trying to make an empirical claim about the nature, and that's why you're trying to use mathematical tools, in this case from computer science, to see the limits of what we're talking about. Okay? This takes us to one famous computer scientist, David Marr. So I'm going to talk about a little bit about David Marr. This is 1977, and then he wrote a book about vision in 1980, and then he passed away very early. It's a big loss for computer science, but he left a legacy in computer science that we continue to practice to this day. So basically he said, well, are we trying to understand an instance of the problem, or are we trying to understand the problem itself? So this is worth writing down. So I'm going to write this. He didn't put it that way, but this is essentially what it comes down to. I'll talk about the way you put it. But basically, the suggestion is if you're facing complex problems, like I said earlier, well, these complex problems are complex they can be complex for two reasons. First, their size is so formidable that it seems very difficult to see the limits of where this is going. It's difficult to see a theory coming out of that to explain all this. But in another sense, complexity means, well, the mechanism and the nature of the problem is so complex that you cannot disentangle the components that give rise to the problem. Okay. And he said, well, if you're going to do this kind of an approach, if you're going to understand the nature of the problem rather than just an instance of the problem, you're going to have levels of explanation for that. And that's going to give you some tools to work with it, like having representations, having algorithms, having data structures. And of course, these things cannot do work by themselves. They're going to need some kind of substrate, like a computer or your brain or whatever, some executive machinery. And even that itself doesn't give you a full understanding of the problem, because it might not give you sort of the goals and limits of the nature of the problem. So his famous suggestion was that not all problems lend themselves to what's called a type 1 theory. A type 1 theory is essentially where you have three levels of Marr explained by the bridge theories and how they're related. In some cases, you may have a type 1 theory, and he suggested that, for instance, vision might have a type 1 theory, but he was also famously suggested that maybe language doesn't have a type 1 theory. Well, 50 years onwards, 50, I'll probably disagree with that, but that's what he said. I mean, you know a type 1 theory sort of when you see one, and it's like giving you, oh, all right, so I can see the relation between the levels. And this is important because if you're going to not study just an instance of the problem, but the nature of the problem, you're going to need a representation of the problem in the first place. So, and that relates to Mars levels. So let's talk about this. So well, let me start in the middle. It's got 3 levels. One in the middle, there is algorithmic level. Implementational level. And what do you call computational level? This is essentially the substrate, the machinery that you're going to need to execute if you have your understanding of data structures. These are like algorithms, data structures, in other words, representation. Okay, and this is the goals of what you're trying to do. What is it that you're trying to explain? So this is sort of like this is sort of one aspect of the how question. How am I going to study? This is like what and how they are brought together, and this is the realization of your what and how questions. Okay. And he suggested that some problems give you just these two, and just learn to live with that because they're not really amenable to explanation. Some problems give you bridge laws and theories between all of these, and when you look at this kind of theories, you say, okay, you've got a type 1 theory in the sense that you're covering everything there is to know about this problem. So understanding and you might be thinking, why do I need this to be able to come to a level where you can say, I'm beginning to understand the problem. Well, think about sorting. Okay. And think about understanding instances of sorting. Right. This is a very, very well-known problem in computer science. There are actually courses called just sorting algorithms. And if you look at this problem from a sort of a Marian perspective, here's what we can do. I can give you 3 objects. Let's say these 3 objects. I have 2 chalks and this, okay? Or something probably bigger to give you an idea. And let's say I'm going to sort them, all right? Now I can sort them by, by their size. But then what is size? I mean, this seems more voluminous than these two. I can sort them by their length. So let's say I'm going to sort them by their length, okay? Now, if you really just interested in these, you can say, well, there's a very simple way to sort these things. Take them out, bang it on a table, like this, okay? And once you, this is too small, let me just give you this one, right? So I sorted them by length, And I can say, well, I just bang it on the table, and because of gravity, they sorted themselves out. And from here on, all I have to do is measurement. This looks taller, so this is the highest. This is second tallest, and this is the shortest. So at this point, um, you bang it on the table only once, and the rest is just measurement. Okay, I just do measurement. And you can say, well, I just solved the problem of sorting by size. No, you can do that, of course. And if that's all you're interested in, you don't actually need an algorithm. You just need nature, like gravity, and it's going to sort it out for you. It's just that if you really understand the nature of problem, now try to do that experiment in space, okay, where there is no gravity. Although they still have the same shapes and sizes, you won't be able to make use of gravity to sort it this way. So in the first solution, I banged it on the table. It's not an algorithm. I'm just using nature and my understanding of nature to sort the problem. And then I read the results because of my understanding of nature. If something is taller, it's in a higher value. Next taller goes like this. But that doesn't give you an understanding of sorting in some other substrate, to use Marian terminology. Okay? So if you go to outer space, you can't do that. Or if what I'm sorting are not rigid bodies, if they're just liquids, I can't bang them on the table to get that result, right? I need to measure their volume if I'm sorting by volume or whatever. That means if you're going to solve these instances individually, every time you come up with a different substrate, you're going to attempt a different solution. Okay? So the idea of sorting in computer science is, well, we're trying to understand the nature of sorting itself rather than individual instances of sorting. So what we do is we map these quantities into some predictable differences. Like, I'm going to map it down, let's say, to numbers. This one I'm going to map to 10. This one I'm going to map to, let's say, 8. And if this is mapped to 10 and this is mapped to 8, this should be mapped to something less than 10 or 8. And if you have a robust representation of these things, then you're going to be living in the world of just numbers, 10, 8, and let's say 5. And whether you're in outer space or here or in a dark corner of the universe, you're going to sort them out in pretty much the same way. Okay. Now, if you think of this problem, for you to be able to tackle the problem like this, you need a representation. Okay. A representation essentially means rather than working on the direct measure of the thing itself, I'm going to map it to a solid representation. Solid in the sense that when you are faced with these, this is mapped to a higher value compared to that one. And if you're consistent with your representations, in other words, level 2 of MAR, then you're going to attempt the problem at the level of the algorithm. And who knows, that might give you a theory of sorting in the long run. It's sort of Mars level 1. And I think it's been achieved in computer science to the extent that once we truly understand the nature of sorting, then we realize that there's a difference between comparison sort and what's called radix sort. Comparison sort, as you can imagine, basically says you sort these things by measuring, by comparing values. Like 10 is greater than 8, so 8 is on top. 8 is greater than 5, so 8 is on top compared to 5, and things like this. But because of our sort of level 1 understanding of sorting, we know that radix sort does not work by comparison of values. It doesn't compare anything at all. they map these values into space where you preserve their properties by this mapping. Uh, and the reason why this is it's a more of an explanative theory is because once you understand the nature of the sorting itself, you can come up with the idea with predictions about what you can do with this. For instance, the zip code is essentially arose out of the idea of a radix sort. Instead of sorting letters by trying to read their addresses, you can give zip codes to geographical areas. And if these zip codes have some distributional meaning that's sort of meaningful to you, you can sort these all out without comparing anything at all. Okay? So so this is one attempt to turn something that looks very sort of direct problem about nature into saying, well, it's about the nature of sorting itself, that you're trying to get to this understanding of what you can do with sorting once you properly understand it. Okay, and that's what science is all about. You make a postulate that was going to give you some possibilities for further discovery. Okay, so so formal study of structure is a bit of this kind. We're trying to understand the nature of structure itself rather than understanding individual structures. Okay, so that's what I'm trying to get at. And to be able to get to that, we need some mathematical vocabulary. And before I move on to that vocabulary a little bit, let me show you the distinction in sort of attitude once you're adopting that kind of strategy. Now you can think of any problem as something that takes input and that takes output, that gives you output, right? And you can think of this for anything, and you can sort of build in any kind of nomenclature here as your problem, like representation of the problem, its algorithms, data structures, its executive machinery itself, and things like this. Okay, if you're only interested in that, then this is a black box for you. And you never worry about what's inside the black box. You just look at input, output, and just keep doing this. Behaviorists used to do that, but it's a long-run tradition now. But you can also look at the same problem by opening this box. Instead of having just the problem itself, you have a model of the problem. And this is a white box. In a sense, and since this is like nature itself doing these things, and you never postulate anything about what's inside. Here, I'm building a model of that, and the model is built by me by using like Marian technology of algorithms, data structures, their automata correlates, and things like this. I can tweak and fiddle with this, and see for unseen input what kind of output I'll get, and whether that makes sense, and whether this model error is from a theory. So okay, so this kind of white boxing, what's inside, requires a very close and detailed look about what can be built as a model, right? And that's what we're going to do for syntax and semantics, and also for uncertainty. So we're trying to turn this into a model building device. In other words, we're going to have some tools and vocabulary with which we can build these models and change them and see if I'm getting some kind of, first, I'm trying to sort of validate my model. I'm trying to see if I can falsify my wrong assumptions and things like this. And once I'm convinced with the model, what kind of discoveries I can make with it. That's the sort of idea. Okay. So how can we enumerate the structures in this this way of thinking? Well, there's one thing about structure. Well, two things. One, it seems to be potentially infinite, and I'll tell you what that means. Two, it seems to be discrete. Okay. In fact, if physicists are right, everything in the universe is discrete, but let's not get into that. But essentially, the kind of things that we can enumerate here are essentially countably infinite, countably potentially infinite, so to speak. And by infinite, usually what we mean in computer science is something arbitrarily large. I mean, if physicists, again, going back to physicists, if they're right, nothing in this universe is infinite either. It just means arbitrarily large. Okay, and if you recall my this example, with just 4 words of English, actually it's 9 words if you ask morphologists, because you as an accusative can be different than you as a nominative. And so, but let's not get into morphology at this point. This is essentially potentially infinite. I can keep doing this without getting out of English. Right? I start with I like you, I think I like you, you think I like you, I think you think I like you, I think you think I think you think I like you, and keep it like this. And you get a potentially infinite fragment of English without ever going out of the grammar of English. Okay, so how are we going to eliminate these alternatives so that I can build a model of that is one question. So we need to with a clear definition of what it means to be discrete and what it means to be countable and what it means to be infinite. So I'm going to do that a little bit. The ultimate mathematical device of capturing infinity is the set of natural numbers. This is the natural numbers. Which is, 0, 1, 2. And the problem here is this dot, dot, dot. What does that mean? Where does it end? Okay. Now, they're also known as counting numbers for obvious reasons. Actually, there is a recursive definition of natural numbers. So you can say the base case is 0. You say 0 is a natural number. Okay. If this is a natural number, then successor of n is also a natural number. Now we need to define what it means to be a successor as a function. And we need to define what a function is. And critically, you say nothing else is okay. So this constitutes everything you need to know about natural numbers. So, for instance, 0 is a natural number. Why? Because it satisfies the base case. 1 is a natural number. Why? Because it's a successor of 0. 2 is a natural number. Why? Because it's a successor of 1, which is a successor of 0. And go on like this. Okay? So you essentially you turn into counting in terms of the function s into a recursive device that gives you all and only the natural numbers. Okay, this is sometimes called, this aspect is called closure, which is implicit in all recursive definitions. You have a base case. This is the base case. This is sometimes called the inductive step, and this is the closure. assume something is natural, like in this case, I know 1 is natural because I just proved that 1 is natural. And then I say, well, if it's natural, then successor of natural number is natural. It keeps going like this, right? So this is the definition of being countable and being essentially countably infinite. Okay. So let me write these down as definitions, because this is critical when we're studying structure. What kind of expressions can be given structures? Well, you have to be able to enumerate the expression in the first place. Okay. So here's something, definition. A set is called countably infinite if it's equinumerous equinumerous means so same size for infinite value. One difference between finite, we call it equinumerous because it's essentially a one-to-one and onto function from A to N. Okay. This means 1 to 1 and onto function from A to N. Okay. And you might be wondering why we make this distinction. Why don't we just call it size? But size, the idea of size makes sense in finite sets, right? If A is 0, A, B, it has only 3 elements. The size of A is 3. But if you look at infinite sets, like even numbers, well, how many even numbers are there? Okay, so it doesn't make sense to talk about size of the set of even numbers. Okay, you can say the size is infinite, but infinite is not a number. Okay, I mean, yeah, we write this to mean that, but that's not a number. Yeah, you can't work with it. Okay. So the notion of cardinality is quite relevant to finite sets, but when you move to infinite sets, and that's what I mean by complexity of the problem. If a problem is complex enough, it's going to have arbitrarily large size of expressions. So you can't really pin them down to this. I mean, think about this. If the set of English sentences in Turkish and English can be enumerated like this as a finite set, then you don't need a linguistic theory. What you have to do is just list all the sentences and you're done, right? This is my theory of English or Turkish. But since we can't do that, as the previous example showed, we need to understand the structure in English grammar and Turkish grammar to be able to understand this infinite capacity, or potentially infinite capacity. Okay. So there are things to define here. What's a one-to-one function, onto function? So I'm going to do this a little bit. What's a function in the first place? So I need to get this out of the way. And instead of giving you formal definitions, they're all the textbooks. I'm going to resort to finite sets and show you what one-to-one and onto means. if this is A, this is B, and these are the elements of A, and these are the elements of B, this is a one-to-one. So just give it a name. If f, this is the function f, takes this one to B, let's just give them names, 1, 2, 3, A, B, C. So f of 1 takes you to A, f of 2 takes you to B, things like that. This is a one-to-one and one-to function. Okay? Just think about this. If I'm mapping this to this and this to that, and that to that, this is not one-to-one, but onto, but it's a total function in the sense that everything in A, this is not one-to-one because I'm mapping this one to that and this same thing, the different element of A to the same thing in B, so this is not one-to, but I'm mapping all the elements of A, so this is total, okay? But as you can see, the images itself does not cover the whole set. Now, is this a function? Yes, this is a function. Okay. What is not a function is mapping, for instance, one thing to do two different things. This is not a function, but it's a relation. Okay. You're saying A, if this is 1, this is A and B, A1 relates to A and 1 also relates to B. For instance, like, you know, I'm trying to think of an example. I have to think of a relation that is not a function, so I'll talk about this later. But I'm trying to make a distinction between what is a function or what is not a function, and what is a one-to-one function and onto function. So let's so this is not one-to-one total. Let me give you an example of function that is onto. This is onto, but not one-to-one. Okay. So as you can imagine, being equinumerous, that is being one-to-one and onto, means there is some kind of homomorphism, you know, having same structure between what you're mapping and what you're mapping into. Okay. So, and that's critical thing for us to be able to understand infinity. So, let's do a bit of an example. Here's a definition. A set is I think we've done this example before. A set is essentially countably infinite if it is equinumerous with n. Okay, I think that was the previous definition. Which means if I give you a set, and if there's a claim that it is countably infinite, you must find a mapping from that set to n. Okay, so take this one. So let's call this set E 0, 2, 4. This dot 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 is a bit annoying, so we're going to have to take care of this. This is even numbers, and how many? If you ask how many even numbers are there, well, as many as natural numbers. And this is the funny thing about infinite sets. Infinite set is a set that contains a subset of the same size. You can't do that with finite sets, but infinite sets have this funny property of being of the same size as the superset. Okay, this is countably infinite, which means show the function from E to n, which is 1 to 1 and onto. This is the only way you can actually show that this is countably infinite, because the definition of countable infinity goes back to natural numbers. Okay? Okay? So how can I find a mapping from E to n, which is 1 to 1 and onto, is the critical question. So here's one. Take f to be mapping from 2n to n. Okay. So according to this, if n is 0, I map it to 0. If n is 1, I map it to 1. If n is 3, n is 4, sorry, this is the set of even numbers. This is 4, then n equals 2. This is 6. As you can see, this is 1 to 1 and onto. I mean, if you take, let's just, if n1 takes you to n, and if 2 to the n2 takes you to n, since 2 and 1 equals 2 and 2 because they're equal to n, it follows that n1 equals to n2. So in other words, this is 1 to 1. Okay? And nothing is left out. Okay? Nothing is left out because for every n, I cover something in the set of even numbers. So this is countably infinite, and you can show the set of even numbers to be countably infinite this way. So if you're going to study even numbers and you want to be sure about the complexity of the problem you're dealing with, say, well, is it really a very complex problem? Do I need some kind of representation to deal with this problem? Well, since there are countably infinite many, you're going to have to do that. And this is one of the ways to start thinking about it. Or think about odd numbers. Again, so I mean, by that I mean always it's like 1, 3, 5, dot, dot, dot. It's just that it does that doesn't give you all the instances of the problem. Again, go back to Mar idea. I want to do something about all instances of the problem rather than just one instance of the problem. So I'm going to need to get to all instances of the problem from the earlier instances of the problem. Well, here's a function from 2n plus 1 map it to n. Okay. This is This is 1 to 1 and 1 to. In other words, it maps everything in a set of odd numbers. You will see, and it's actually total 2. In other words, it maps all the odd numbers. It's going to map into all natural numbers, 1, 2. It's going to do them one by one. And in simply speaking, when n is equal to 0, this is 1. So when n is 0, this is 1. So this is 0. When n is 2, when n is 1, sorry. One is mapped to 0. Right? If n is 0, then this is 1, mapped to 0. For 1, this is 3. For 2, this is 5, because n is equal to 2, and this is 5. So you're going to see that this is also 1 to 1. Right? Now, at this point, things look a bit easy. But once you get into slightly more interesting problems than just even numbers and odd numbers, you might think the problem is not so easy. So let me give you an example from previous lecture. Again, take 4 words. Let's call this set 4. Like I, you, think, y. Okay. And then I say and here are the instances of the problem. I'm interested in this language, L4 language, so to speak. I like you is in the language, of L4. I think I like you is in the language. This is language of L4. So you can see where this is going. This is a countably infinite set. What if it is countably infinite? I want to be sure that the problem I am dealing is worth the effort of looking at it in a very complex way. So I want to be sure that L4 is countably infinite. Okay. Now, okay. So this may look a bit non-trivial because you need to find a mapping from L4 to E, to natural numbers. Okay. But here's the problem. You can say, well, yeah, let's just count the things. So the size of this, since this is an infinite set, you can say, well, the size of this is 3. This is how you should represent cardinality of a finite set. This is called cardinality of A if A is finite. This notation makes no sense for an infinite set, but it's fine for finite sets, and the expressions themselves are finite. So the size of this is 3. The size of that is 5, but the size of that is also 5. So you begin to see this. The size of this is what? 7. So although you have the intuition that this set is infinite, showing it formally, remember when I made the distinction, what does it mean to be formal? Well, formal means related to form. It also means rigorously studying the structure. And if you're going to start studying the structure rigorously, you're going to have to make sure that this is worth doing that. The problem is complex enough that you want to tackle it in a very open-ended way, with its limits shown clearly. But apparently, if you do it by number, these things, just simply counting the words in the expression, this is not going to be one-to-one, because this is going to be mapped to 5. This will be mapped to, if your idea is to map the length of the sentence to n, this is not going to work because there are 2 things mapped to 5, similarly more than 1 to map to 7. So this trick, you might be thinking, well, maybe this is not, it's not possible to show this. But think about the set again and begin to structure that set. And you can do this by form. Now, if you form the equivalence classes of L4 by length, then I think I like you and you think I like you will be in the same equivalence class of having the size 5. Okay? So you can think of like this. Here is the I think I like you example, or I like you as one set, and I'm going to map this to 3 because it's got 3 elements in it. And here is I think I like you and you think I like you as one value of the equivalence class, because after all this set consists of union of these. So I can write the union like this, and you can keep doing this. The common property of this equivalence class is having the size 5. Okay. Let's call this G. The equivalence class is called G. Okay. So members of G are essentially this one, that one, and other like length of 7 and whatever. Now we can do a mapping. You can say G is taking things of this and map it to n. When n is 0, you get that for 3. When n is 1, this is 5. When n is 2, this is 7. Okay. And this is one-to-one and onto and total. Why? Well, this bit is a bit difficult to show at this point, but if you look at I think I like your language, you're going to see that the common property of that is that all strings are of length 3, 5, 7, 9, and things like this. Okay? This is a very crude linguistic theory about the structure of I think, I like you at this point. But since we're interested only in the formal properties at this point, this is fine. And I just showed you that if you think of this set as a structured set, consisting of set of sets, then you begin to see what's common in I think, I like you, and you think, I like you, and you can and you can say, well, yes, if you keep going like this, you're going to get a countably infinite language. So this is worth seriously looking at, because the size is just too big to be able to enumerate all the examples. Okay. So this is one way of capturing potential infinity using finite means, to use a finite von Humboldt terminology from 19th century. And at this point, it gives you at least a foothold in studying what Barr was getting at. Look at the problem. Is it worth looking at it from a perspective where you're not only interested in the instance of the problem, but you're interested about the nature of all instances of the problem? If you're going to do this, you should be able to enumerate all instances of the problem and then do something about these instances. That's how you understand the nature of the problem. And if it's an explanatory understanding of the thing, you're going to have a type 1 theory in Marr's sense. Okay? So what is an equivalence class? I need to define that, and I'm going to stop for today. Maybe I should continue. Let me see. Yeah, this is a good place to stop. So let me just give you an idea of relations. We usually write like A related to B. For instance, 3 is less than 5. Okay. Well, this is a relation in the sense that many things are less than 5, right? A relation is transitive if A relates to B and B relates to C, then it follows that A relates to C holds. So this is, for instance, transitive. If 3 is less than 5 and 5 is less than 8, then 3 is less than 8. Okay? A relation is symmetric if A R B implies B R A. Example, this is not symmetric. But equal relation is symmetric. If A is equal to B, then B is equal to A. But this, if 3 is less than 5, then 5 is not less than A. So this is not symmetric. Okay? And a relation is reflexive if A R A holds. So, for instance, this is not reflexive. But equal relation is accepted if A is equal to A, 3 is equal to 3. Okay? So, but this is not reflexive. because 3 is not equal, 3 is not less than 3. Okay. So an equivalence relation is a relation which is symmetric, transitive, and reflexive. Okay. So in the case of our example, having a length of 5 is transitive, because if some expression has a length of y, if another expression has a length of 5, then they are in the same set of equivalence class. It's reflexive because if an expression has a length of 5, then it has a length of 5. And if A has a length of 5 and B has a length of 5, then you're in the same set. Okay. So in that sense, they give you an equivalence class. And for instance, having the same length at this point is an equivalence class. Okay? And that's why equivalence classes are nice in the sense that they partition your set into disjoint sets. And that's why you were able to prove that your L4 as a set of sets mapped one on one on one. Okay? Instead of taking the members individually, I formed the equivalence class. And since this equivalence class constitutes the whole L4, I'm covering my whole set, but I'm just mapping from sets of expressions to a number rather than expression to a number. Okay? So that's the big difference, and this having a representation gives you this possibility. You can think about mappings, you can think about how these mappings that you require to hold restructures your domain. And you can say, well, what else is interesting about this set? And things like this. You think about like, why is think doing this and like not doing that? Yeah, it's an interesting property, right? You can say, I think I like you. But you can say, I think you. So if you're only interested in size, this means ungrammatical. It's not in English, it's not in L4. It has a length of 5, but I'm not interested in that because that's not English. Okay? So once you structure your sets, and you say, okay, length 5, but this just shows you that it's not good enough. A metric like length is not good enough to understand structure. You have to rise above if you're going to understand structure, you have to rise above a metric to understand it. Okay? This has length 5, well, this one has length 5 too, so why are you not including that in grammar? But it's not English. So you need to study, well, what is it that think does that like cannot? Okay, so you begin to think about things like this, and that's going to give you structures and substructures, right? So I'm going to start doing that next week, and then we move on to formal description of that in the form of formal languages. Okay? At this point, a language to us is just a set with certain properties. So if it's an interesting problem, then this set has interesting properties, like being in English, not allowing this while allowing that, and things like this. Okay? So for a mathematician and computer scientist, a language is a set with certain properties. As a cognitive scientist, well, you might be thinking, what is it about these properties that structures the set? You would be interested in that. And that's going to take you to sort of MAR territory. Okay? So I'll start doing that next week. So stay safe and see you soon.